All right. When we last left off, we were going to talk about geometric pitch. And I was going to, like, look at what you had in your class and do this great job, but then I forgot all about it. So at least I'm honest.
What?
I was going to prepare something here for you, but then I totally forgot. So
You've been winging it this whole time?
pretty much, yeah. You just figured that out?
That's what I do during the oral sometimes.
Okay, so geometric pitch is defined as how far the plane would move forward if the propeller had no slip and was 100% efficient. So you take the angle, what the angle is, and how far it's going to move forward. So it's a mathematical thing. So as I have it here in my notes in front of me, I have geometric pitch equals 2 pi times r, and little r is the radius at the 75% station. Now that's an important thing because when you're talking about propellers, that is the spot where these measurements are taken from, if you ever have to do it. So it's the radius at the 75% station. Radius of the 75% station at 75. Okay, radius times tangent of blade angle. Tangent, yes.
I'm gonna be that guy. Why? Any idea why it's at 75%?
The Geneva Convention of 1968 met, and there was a huge. The delegate from Netherlands wanted it to be the 68% station. The Germans insisted that it was, I don't know. All right. So I have an example. Let's see what happens here. Example. Let's just say we had a blade, a certain blade, has an angle of 20 degrees. I don't know, right? It's at station 30. So what does 30 mean?
30 inches from the center.
30 inches from the center. If we wanted to do our math, we could figure out how big the prop was and all that, but I just gave you the 75% station. Oh, I did do it because when I wrote my notes. So if we were doing it at station 30, actually I could, let me see. I could have done it like this. I have an angle of 20. I'm going to make it more difficult, at the 75% station, and the prop is an 80-inch prop. There we go. So, what is my 75% station? 30. How'd you know that? Okay, this is the thing, though. It's going to be on the test. I need to know the 75% station. What's 80 times 0.75?
60.
60. Well, then how come it's not the 60% station? Or the 60 inch? Because you got to go 80 divided by 2 is 40 times 0.75 equals 30. And I guarantee that'll be on the test. And I guarantee you that the correct answer for 80 times 0.75 will be on there. And you're like, sweet, I got it. And you won't. So 30. All right, so let's see here. So that would mean that we fill this in, the geometric pitch equals 2 pi times 30, the radius, the 75, or the 75% station, I think is a nicer way to put it, makes more sense. 30 times tangent of the blade angle. So that's 20, or tan 20, which equals what? Because you have the calculator, I didn't bring one. What is tan 20? 0.364. 0.364. So we do the math. It's actually 0.36397. So that would mean the geometric pitch is 6. Where did I get 2 from? 6.283 times 30 times 0.364. All of that is going to be geometric pitch equals, what'd you get?
68.6.
68.61 inches. What does that mean?
Plane moves 68.61 inches forward for every rotation of the grid.
The plane will move forward
68.6.
almost 6 feet every time it turns around.
Theoretically.
In theory. So that is called the what?
Geometric pitch.
Geometric pitch. So this is the distance the aircraft would move forward. This is the distance the aircraft would wish that worked. It does. Would move forward in 1 revolution of the prop. All right, so that is geometric pitch. But then we have a thing called effective pitch, effective. And that is the actual distance the airplane moves forward. Moves forward in 1 revolution. One revolution of the prop. So effective pitch can range from 0% to 85%. Why 0%? Got the brakes on, it's 0%. So you can go all the way up to 85%. So that means it's not 100% efficient, it's 85% efficient. Best case scenario according to this right here. And obviously we should realize, I'll just put these points down here since there's just kind of, if we have a small blade angle, that is going to be less distance per rev, right? And we have a large blade angle. We equal more distance per revolution. Well, if that's true, how come we just don't bend blades and put in a bigger angle so everybody can go fast?
And limitations of blade tips.
Power requirements. That's kind of like saying, well, Cooper's car does what, 85?
85 miles an hour or 85 horsepower.
Who has a stick shift? All right. So, you know, not you, but if somebody else was driving your car, how fast would they go? And what you got, 5-speed?
Yeah.
Yeah. You got 5th gear. What are you doing?
Like 85. Like
85?
if that.
Well, you could do 200 miles an hour if we just geared it better, right?
Yeah.
Okay. So, but that wouldn't work, right? Because, well, if you've ever dealt with the manual, you get up to these higher gears and there's not a lot of, you know, you kind of got a floored there just trying to get it to going. So same thing. So there's just not enough power in the engine to do that. And so it'd be like trying to take off from a stop sign in 5th gear. Just doesn't work. That's why there's a 1st, a 2nd, a 3rd, a 4th, and a 5th, because you got to get it in there. So can't just take a blade and just pitch it so much. So if you over pitched it, how would I find out if a blade was over pitched? Too much. There you go, low static RPM. I go out there, static RPM, feet on the brakes, wide open throttle, and I've got like 1,000 RPM. Think that's a problem? Yeah, try and take off with that. It ain't gonna work, right? And so if I have low RPM, what does that mean for horsepower? PLANK. It means low horsepower. So instead of having a horsepower that maybe had 200 horse at 2,700 RPM. Now I've got an airplane that's only giving me 50 horsepower at 1,000 RPM. That's just not going to work. You got to get the speed up to get the horsepower. You guys know that.
Would that hurt the motor? Like if you're trying to
Oh yeah, yeah. High manifold pressure, low RPM. That's bad for it. So yeah, you got to consider the pressure in the cylinders goes way up because the valve is open for so long because it's moving. The pistons are going so slow that all of the air has a chance to get in there, really fill up that cylinder, lock it down, start to compress it. It's like, wow, that's a lot of air in there. All right, so then we have CF geometric pitch, which is theoretical, effective pitch, which is actual, and the difference is slip. The difference between the geometric pitch and effective pitch.
Is there any correlation with downward and maneuver? Slip?
No. So geometric pitch, GP, minus effective equals slip. Why is this important for you to know as an airplane mechanic?
It's not.
It's not. What is important to note is how a propeller and the engine combination react to what's going on. Because you have to understand this. Number one, we've talked a lot about static RPM. If you're going to work on something with a propeller and a piston engine, the fixed pitch, you have to understand the static RPM correlation. And then you have to understand what happens to the propeller as you start to roll down the runway, no matter what propeller it is, no matter what you're working on. If it's got a prop, you need to understand that correlation. So I'm sitting there at the end of the runway, got my feet on the brakes, and I go wide open throttle. My RPM is going to seem a little bit low, right? Remember, as my friend used to say, who was a pilot, you're dealing with dumb pilots. So it's like, my RPM is low. I got a red line at 2,500. I'm on my brakes, wide open throttle. It only gets 2,100. Why does it only get 2,100? It's your static RPM. Why is it low?
Too high angle of attack on the blades.
Angle of attack is really high on the blades. So it's not efficient at all. It's just whacking it on the face of the blade. So it's not working. Take your feet off the brakes and start to roll down the runway. What's the tachometer going to start doing?
Going up.
Going to start climbing. Why did it start climbing? Because the angle of attack changes. The prop becomes more efficient. So you're talking to a pilot, and they're like, yeah, something's wrong with my engine because, when I'm sitting still, I have a really low RPM, and then when I start to roll and I get ram air coming into the induction system, it goes up a little bit. Is they right or wrong?
Well, they're right.
Is
It
it
sounds
wrong?
like they're saying something that's.
Sounds like you're saying something right, but is that what's causing the RPM to go up? There's ram air coming in? Now I'm using my dumb guy voice. Hey, ram air is coming up. Get her done. So, no. Why did the RPM start rolling up?
Because the angle of attack.
Because angle of attack. That's what it's supposed to do. So he wants you to fix it. What are you going to do?
Charge him and then not do anything.
Yeah.
Diagnostic fee.
Yeah. Couldn't find anything. Could not duplicate on ground. Okay, we got that? I know we haven't talked much about constant speeds yet, but I'm in a constant speed propeller, and I'm at the end of the runway, and I have my feet on the brakes, and I go wide open throttle. What am I going to see RPM wise?
Nothing.
Red line's gonna be red line.
It better be red line,
Wow. Should change.
right up to red line. And now I hear, because where my hangar is in Lodi, I can hear people taking off all the time, and that's not generally speaking how you take off, especially in Lodi, because there's a lot of loose gravel and stuff on the ground. I hate it. So you need a rolling start before you add a lot of power. So smart person's kind of just enough power to get rolling. Then once you're rolling, go ahead and push that power all the way in, and then you hear the prop go. You can hear the engine go up in RPM and back in RPM. What happened? It overshoot. It overshot the red line because the governor is working. We'll talk about that. He has cold oil, so it takes a second. So the engine oversped, and then the governor caught up and brought it back. So don't do that. All right, let's see. I did call this aerodynamic forces, but I crossed it out and I wanted to call it prop forces. I don't know. We can call it prop aerodynamic forces. Oh, I know why. It makes it prop forces. That makes sense. I know why. But before I do that, I think I have slides here. Let's see. So look at these slides. You remember that one?
Yeah.
Well, that's the same thing, but it's just different. So I don't want you yelling at me about this one. So okay. Low pitch, high pitch, right? So if I take a blade and I pitch it with more bite, I'm going to go further per the RPM to a limit, as long as the airplane can handle it. Same thing, just different color slide. All right, geometric pitch. Geometric pitch, so we're starting here. Geometric pitch is, I don't know what that should, oh, how far it should have went, all the way up here to the shadowed. Should have went to there, but instead it went to here. So, difference is slope. All right, our forces, prop forces. We're going to have 5 forces. 1, 2, 3, 4, 5. Prop forces. First one is centrifugal. Centrifugal force. These forces are going to become very important when we start talking about constant speed props. And you need to understand the forces, because the forces are what we're going to use the forces to actuate the propeller. So the centrifugal force is a force that tends to throw the blade away from the hubs. Sometimes that works. There you go. From the hub. I said hubs, but it's hub. It causes a stretching of the blades. Makes the paint slide off. It is the greatest force acting on a prop. It may exceed 7,500 times the weight of the blade. Somewhere I saw it's like 20 tons or something like that. It's a lot. And if you haven't lifted this up, it's actually not very light. So 7,500 times that blade weight, trying to rip it out of the blade hub and take off. So that is why I do not stand in line with blades that are spinning, because if it decided to leave, which I've never heard of one doing it, it'd be just my luck. Whoosh. Then you'd have something to tell people. Remember that time we were at AMTP school and that one teacher got his head? Yeah.
Catch it.
Right, so it's trying to rip the hub is the middle part, so it's trying to rip the blade out, right? It's actually going to stretch them out. Next one is, and it's the most highest force. Let's see, torque bending. So due to air resistance, tends to bend the blades in a direction opposite rotation. C, thrust bending force. That is the thrust load that tends to bend the blade forward as aircraft is pulled through air. Representation. Centrifugal force. Blades are being ripped out of the hub. Torque bending force. Propeller is going this way, and it tends to kind of bend them back the other way. And thrust bending, where it tends to pull the blades forward. So those don't have a big effect. They don't have an effect on how propellers work. It's just you have to be aware of these forces. And the thing that I guess I've kind of learned over the years is it's funny how heavy props are, how strong they look, and how weak they really are. So in one respect, you know, they're strong. It's 7,500 times the force trying to rip it out of the hub, and yet it doesn't. But yet you can easily break them. So you want to see me get real excited? Touch my propeller. It sounded dirty. Don't touch my prop. I hate it. You will actually bend a blade and ruin it. When you're pushing airplanes around, I see people doing it all the time. They'll push about right here, and they're just pushing on the airplane. Guess what that does? It bends the blade back. I was talking to a prop shop. They said on really hot days and stuff, people doing that, you'll ruin the blade. So, huh? Well, if you're going to do it evenly on both sides. How come your propellers curve backwards? That's a special thing. Yeah, not only that, well, people tend to, when they're doing it, so I will push on my blade if I absolutely totally have to, and I have no other choice to move my airplane, but I'll only push like right about here, right next to the hub. But when other people do it, I've seen them do it, and they put stress on the spinner, and the spinners break. Now, you want to talk about stupid expensive parts. A new prop for my airplane, and my airplane's small, I don't know, the 2-blade I think is like $10,000, $12,000, but the new 3-blade with the hub is going to run about $20,000. I mean with the spinner, not hub, that comes with the hub. So, yeah, a new spinner assembly with bulkheads is something like $10,000. Yeah. Yeah, somebody broke the one on my 150. I sent it out and had it weld repaired by a specialist in welding aircraft spinners.
Welding certs with the FAA.
What's that?
He had his welding certs with the FAA.
His JB weld cert.
Yeah.
He did, and it came with an 8130, which you guys will learn about in second year, which meant it was an approved repair. So, okay, so don't push on the prop. In fact, my daughter-in-law actually yesterday sent me a video she was on Instagram or something of somebody moving the plane, pushing on the prop. She sent it. She goes, "This will make you mad." So my daughter-in-law knows how much it bugs me. So, all right. So don't do that. Don't bend. Don't push on the prop. I was talking to a prop shop one time. So obviously we have constant speed props. It would make sense that they need an overhaul. They have moving parts. But what about a fixed pitch prop? Yeah, they need overhaul too. Well, what are you going to do to a chunk of metal? Right? How do you overhaul that? What's that?
Sand it?
They do. They sand it, and that takes out this because the stresses rise to the surface. It takes out the surface tension stresses. They will do a repitch on it and balance, and they say that they get way out of whack. They said it's crazy how some people have reported how much speed they've picked up on a prop that's just been overhauled versus one that's been on the plane for a long time. The forces get out of whack on it, and so anyway. Okay, we are thrust bending force, did that one. Now, these two are different. In fact, they're so different that I actually cut that and put it on sideways. It drives me nuts. You guys, well, you don't read the book, but if you did, you would know that. I'm just kidding. All 5 of these are all lined up. And it's like, well, these don't make any sense. Why did they put the hub facing up? So I put them the way they actually go. This is the hub. You follow what I'm saying? Yeah, they don't belong. It's not a helicopter. Sorry. So anyway, these two over here are important. The Aerodynamic twisting force, not to the greatest extent, but centrifugal twisting force is probably the most important force that we deal with when we talk about propellers from a standpoint of how they work. So we have aerodynamic twisting force is one. It tends to twist to twist the prop toward a high blade angle. So it's going to get confusing as we start talking about blades. High blade angle, low blade angle. So one thing I want you to get in your head right now, and this will make it easier, is in a constant speed propeller, the blade rotates. I've got it right here. This blade moves back and forth, and it's like this. So it's going to move back and forth. Not a great deal, because we already learned that 1 degree is like 60 RPM. Yeah, so it's not a great deal. This is in my way, so I got to move that. I'm on mic stand. I was doing karaoke when you guys were around. If you have a twin engine aircraft, doesn't matter if it's got props on it, piston, turbine, whatever, if you got a multi-engine aircraft, the props have to feather, which means this blade goes all the way forward and faces into the wind. So normally the blade is going to be, on a plane looking like, I should do it so you can see it like that. But if we lose an engine, we want to be able to feather. And that means the blade's going to be able to roll just like that. And so the air going forward is going to hit it like this and not cause the blade to windmill. Because we do have to think about the blade as moving around in a circle. So as it moves in a circle, it is a disc. It acts like a disc. And so if I'm flying along in an airplane and I've got a disc that's 7 feet across and I stick it out in the wind, that is a massive amount of drag. So if for some reason the engine quit and we couldn't feather the blade, what if the engine is having a catastrophic disassembly? Right? The engine's going to keep windmilling and it's going to get worse and worse and worse and shaking. You got to stop that engine from spinning, so you got to go into feather. Okay? So you got that going. You lose oil pressure. Well, if you lose say an oil line blew, do you want that engine sitting there windmilling? No, you want to shut it down and protect it. Oil pressure starts going low. You're like, whoa, losing oil pressure, shut it down, feather the engine. It's the same thing as you parked it on the ramp. It doesn't care. So now you've saved the engine. Land, change out the hose, add some oil, you're good to go. But if it keeps spinning, you're going to ruin a bearing and the end crankshaft and everything. So you have to be able to feather. So that's the term all you know, feather. Feather is when you go aerodynamic all the way that way. That's the highest of high pitch, right? Yep. So I'll say towards feather. So I can say high blade angle towards feather. Low blade angle towards flat or zero. So I'll say flat. So flat, feather. So you got that? So aerodynamic twisting force is going to, because of the way the center of pressure is versus the center of rotation. I don't know why center of rotation here when it actually rotates there, but that's the way wings work. Aerodynamic twisting force wants to rotate it towards feather. Tends to twist the prop towards high blade angle, which is feather. Y, center of pressure. Center of lift, pressure, is forward of center of rotation, which is the midpoint of the chord line. So because of the way this aerodynamic, the forces go over the blade as it's spinning, it wants to just twist it towards feather. That's all you need to know. Almost doesn't matter because it's not that great of a force when compared to centrifugal twisting force. So due to the mass of the blade, this force tends to make the blade go to a flat angle. So I can't do it like in this plane, but I can do it this way. So if I take this blade and I kind of hold it like this, you want to duck because I'm going to spin around real fast. You're going to see that as I spin real fast, it's going to want to naturally go this way. So sometimes I lose it. So you guys ready? I'm just kidding.
I'm waiting, I want to see it. Let's go.
Oh, look, see, I told you. But it does. So because of the way the blade is, the mass wants to flatten out as it's spinning. The mass doesn't want to do this as it's spinning. You would think that would be aerodynamic force. It want to go into that, but it doesn't. Aerodynamic force is going to make it want to go to like this normally, or like this normally. Aerodynamic twisting force makes it go towards feather.
The most aerodynamic position.
I said, wait, that's aerodynamic. Aerodynamic forces want to make it go this way. But as it's spinning, centrifugal force wants to line it up and make it go
That way.
and this one wins.
What's the weather thing?
It's not really weather, it's centrifugal, it's weight. Weight does it.
No, I mean the aerodynamic twisting force. It's like weather thing.
So you can try it like this, put your hands like this and spin around. They'll go like this. So flatten out. So, all right, so it makes it want to flatten out. And the two centrifugals are the greatest forces of all. So that means that centrifugal twisting force, which is the only one that can really make the blade move, is always going to win. Due to mass of blade, force tends to move the blade toward a lower blade angle. Flatten out. If it's a fixed pitch propeller, what does it do? It'll bend a little bit. You know, it can't move much. It's sort of fixed. So the centrifugal twisting force, which shall forevermore be known as CTF, because I'm not writing all that anymore. Centrifugal twisting force is greater than aerodynamic. Twisting force, or ATF, which I never say, because we don't talk about aerodynamic twisting force after this, because it just isn't strong enough. So CTF is used to control constant speed props, which we'll talk about later. Now, if we're going to talk about props and talk about spinning, one thing we're going to talk about is tip speed. So tip speed, it is a principal limiting factor for propeller efficiency for prop. I'm going to say and speed. Why is speed an issue?
Can't go supersonic.
Can't go transonic. Once you start getting there, you're going to set up a pressure wave that is just going to run down the prop, and you can actually start losing pieces of the prop. It's not just inefficient at that point. It sets up stresses that can rip it apart. So excessive speed causes flutter and vibration. So funny story. A couple months ago, I was up at Auburn. You were there, right?
Oh, yeah.
Yeah, so we were up in Auburn. I think it was there. And I was talking to this guy, and I told him what I used to do. And he's like, oh, I remember. He goes, you built the engine in my RV, my home built. And I was like, oh, awesome. How is it? It didn't last worth a shit. Great. That's not what I wanted to hear. He goes, yeah, the thing just didn't last. And had it overhauled, and it didn't last. Funny thing, Kevin, I didn't know that engine and propeller combination that I put together had a significant vibration area right in the middle of where he operated it nonstop. And it ate itself to pieces. And he went through like 3 engines before he figured it out. Yeah. So in a certified aircraft, so an RV is a home built, in certified aircraft, you will see that sometimes, and I think I have notes in here to talk about that, where it will be placarded, do not operate in this range. You can go through it up to here, you can go through it down to here, but you cannot stay anywhere in there. And so when he researched it after a couple of engines and looked at what airplanes, certified airplanes had this engine and that prop combination, it was placarded to never run in this area. And he said that's exactly where he ran it always, all the time. And it didn't work out so well for him. He said, other than that, the engine was great. Like, sorry about that. So tip speed must be below speed of sound.
I think while you're also going through that transonic range, you start losing lift.
Oh yeah, yeah. These, well, they're not supersonic airfoils, so that would. So let's see, supersonic speed 1116.4 feet per second, or 761 miles per hour at sea level. Not the, yep. Not that it matters. I'm not going to ask you that again, but just in case you cared.
I don't know if it's a dumb question, but do they make transonic airfoils?
I bet Nick knows. They ever made? I don't think they did. I don't know. Have they?
They tried one,
But it
and
didn't work
it
out.
was, the test pilot said, you're not big enough, and there's not enough of you to get me back in that aircraft.
And the sonic waves that it produced, even on the ground, knocked out multiple people.
Oh wow.
Yeah, it was like they
Oh
had
my
they
God.
kicked them out of the airport, and I think they had to do everything 5 miles away from any.
Jeez.
So yeah, it was bad.
Plus
Plus
a
jets
little bit more
jets-
horsepower, or way more better for that anyways.
Way more better.
Yeah, it was. I must have been right about the jet age.
Yeah,
Yes.
So props are actually more efficient at lower altitudes. So that's why you still see prop planes, and why we're not flying around jets at low altitude. Jets are better at high altitude. And of course, then you can add that. This is an uneducated note, but when you look at the new modern day jets, they're just gigantic ducted fans, which are ducted fans to me is just a propeller with a shroud around it. So these props are just better all the way around. There was a really fun point I was going to make there about something. I don't know. Oh, yeah, you can hear planes take off with constant speed props that they've got to be getting close to that transonic. You can hear them cracking. They're just, you'll know. If you're hanging around an airport, right, you guys know what I'm talking about. It's the constant speed's like 182s a lot of times. I have a lower spinning 182, but the ones that have the higher RPM, you can really hear it. It's just an obnoxious noise, and I think it's somewhere near that. Let's see. So to prevent something from prevent tips from exceeding sonic speed, what do they do? What can you do?
Prop governor?
Okay, we can say, well, limit RPM.
Higher angle, and limit the diameter as well.
So limit RPM. There you go. Shorten the prop.
Speed.
Shorten the prop. Everybody knows why, right? Shorten the prop. It's not going as fast. Same RPM, but it's not traveling in that circle because it's way out here. It has to travel faster than what's in the middle. So you can shorten the prop. What else can you do?
Change out, you do the
Gear reduction. Rotax. They're spinning the hell out of those things. They reduce it way down and spin the prop slow.
Increase the blade angle.
That wouldn't.
That would lower your.
Are you thinking because it'll lower the RPM?
Yes.
Well, I said that. Limit the RPM, number one. But if I have a constant speed prop, I wouldn't. I mean, it would, I guess. The low pitch stops or something. But no, it'd just be limit RPM. Let's see. Propeller loads. Propeller load. Let's see. I thought this was interesting. The faster the prop turns, the more power it absorbs. The more power it absorbs or uses. I don't know. I could probably get rid of this whole note here, but since I started, varies with the cube of RPM. So in other words, I'll put down here, double the RPM. Go from 1,000 to 2,000. That's going to equal 8 times the power. 8 times the power.
So you're saying that the faster they go, the more efficient they are, but until you reach.
I just thought it was interesting that you would think that if you just went from 1,000 to 2,000, you doubled the RPM, you would double the load on the prop. But it was really 8 times the.
Oh, the load.
Yeah, the load on the prop, which I just thought was interesting. So I thought, I'm going to put that in there because I think it's interesting. All right, efficiency. Let me see. I wrote, maybe leave out. Yeah.
All right.
But that's all we care about is efficiency, man.
Oh, well, I can tell you what I wrote. So efficiency, I wrote thrust horsepower.
I got a question. I heard, I don't know if this is true, this might just be hearsay, but somebody told me that if you prop strike a wooden prop, you don't bend your crank. But it's kind of like a wooden prop can absorb more.
Yeah, I object.
Actually, that's an interesting point. So that is true. If you have a metal propeller and you hit something, in fact, I was just listening to Ask the AMPs the other day, and that was a subject they were even talking about. Somebody hit a traffic cone, and you hit a traffic cone with metal blade, it'll send it sailing pretty good. But if you hit something with a metal blade and you have to take the propeller off to have something fixed on that blade, that is a prop strike, which means the engine must come apart. You want me to wait for you to finish that talk?
Sorry, that was my sister.
That's all right. You're trying to hide it, but you're sitting right in front of me.
Oh, no,
You're just
I-
better off just putting it on your desk and doing it.
I was putting it away. And
That's fine. All right. But if you have a wooden prop or a gear reduction gear like Rotax, they say you get a prop strike. So what? Do a gearbox inspection. Guaranteed your crankshaft's fine. Don't worry about it. Then you get a wooden propeller, and it will usually protect the crankshaft. I just remembered that I had a person with an A65, A75. They sold their airplane, and the new owner ran it up the back of a BMW and had a wood prop on it. And man, did it make some toothpicks. But we still had to do a prop strike. I mean, there's nothing left but the hub. And yeah, but the crank was fine. So yes, if you have a wooden propeller, chances are you're going to do a prop strike. Chances are crankshafts can be fine. Actual amount of horsepower, that, and engine, propeller, engine, prop, unit, that's thrust horsepower, transforms into thrust horsepower. The things I'm not going to then tell you, or let's see, 8, 9, 10, I wrote, maybe not. Thrust is perpendicular to the rotational plane of the prop. Brake horsepower, torque, actual horsepower delivered to the prop. And propeller efficiency, which is thrust divided by torque horsepower. We don't need that.
I agree.
Yes. All right. Let's take a break on this one. Then we can, because this is a good stopping point.